Welcome, my name is Wim Willems. My talk is about DVS, an experiment where the time-dependent wood moisture uptake is recorded by weight changes after a relative humidity step in the ambient. My study focuses on the conditions wherein the moisture uptake rate can become controlled by heat, which is released when water vapor condenses into wood. Here is a set of moisture uptake curves from this classical study of Christensen and Kelsey. Ever since their 1959 publication, it has remained a question why the uptake rate is depressed at high RH. The associated heat exchange is evidenced in wood temperature elevations, but these appear only peaked at the very beginning of the moisture uptake curve. With increasing RH, the peak temperature is strongly reduced, and it was therefore concluded that there is no thermal origin of slow kinetics. However, that view is incomplete. Besides the induced temperature elevation delta T on moisture uptake, there is also a consequential effect of delta T. Delta T decreases the local relative humidity around the sample, resulting in a lower EMC, which influences in turn the moisture flow to the sample. A final EMC can only be obtained when delta T becomes zero, which essentially requires an efficient heat exchange with the ambient to get rid of all accumulated heat. I assigned the name thermally limited moisture transfer to this mechanism, which is analyzed in the developed physical model that rigorously calculates its dynamics. The rate model can be exactly solved. First, without heat-moisture couplings, one finds a simple first-order response. And after adding heat-moisture couplings, a similar response is obtained, but with a timescale factor. In a graphical representation, the response is increasingly time-stretched by a stronger heat-moisture coupling factor. This factor is calculated to be unity at low RH, giving no effect, but increases strongly at high RH, yielding a retarded response at high RH. The predicted theoretical RH trend of the timescale factor is a linear function of the product of RH times the slope of the moisture sorption isotherm. This linearity is indeed confirmed by DVS data, with one example given here. So the simplest possible rate model for coupled heat-moisture effects explains the reason for slow kinetics in small wood samples at high RH. The thermally limited moisture transfer model appears to work despite drastic simplifications because the mechanism acts via the variables in the ambient domain, relatively independent of internal wood moisture transfer and relaxations. Without further explanation, I just mentioned that for the opposite direction of moisture change, wood drying kinetics are also retarded at high humidity by the same mechanism as for moisture uptake. I want to conclude this talk that the effect of heat on moisture dynamics is counterintuitive, namely a large thermal peak with little effect on kinetics at low RH and a small thermal peak with large retarding effect on kinetics at high RH. The mechanism acts in heat and moisture transfer processes at the boundary between wood and the ambient and can easily be incorporated in existing numerical wood moisture transfer models. The described mechanism suggests the importance of a proper thermal design of experimental setups where the wood moisture content is supposed to change, notably at high RH. The thermal effect appears to have a time-scaling action on the entire moisture response curve, which might be used to remove thermal effects from DVS data, which work is in progress. Thank you for your attention.